Alright, I'm going to go over the flipbook problems again. We didn't plan on doing a podcast, that's why it's just me. Ms. McClendon wasn't able to join me today. And so, but several of y'all have asked where it was, so I'm going to go ahead and redo those 6 problems with y'all. The first problem deals with molarity, so you have your big M, which is your molarity, equals moles of your solute over liters of the solution. So when you look at a problem, here's our sample problem. You have to underline what you're given. You're given 0.9 grams of sodium chloride. You're given 100 milliliters, and you want to know the molarity. So looking at our formula, we don't have anything that is in here. We don't know our molarity. We don't have moles, but we can get to that. And we don't have liters, we have milliliters. So we're going to have to convert that. But the first thing we have to do is change our 0.9 grams of sodium chloride to moles. So we divide by the molar mass off the periodic table. And that's 58.4428. And that gives us 0.0154 moles. Okay? So then we can plug that into our formula. So we got 0.0154 on top, and then we change our milliliters to liters by moving the decimal 3 places. The magic number for chemistry, most chemistry problems is 3. You're moving your decimal 3 places if you have to move a decimal. So that becomes 0.1. We divide that out, and that becomes 0.154, and we're talking about molarity, so that's a big M. Well, usually in preparing solutions, you're actually working in another direction. You know how much of what type of solution you want, but you don't know how to make it. So when we want to make a solution, we still have to figure out what all we're given. We got our 200 milliliters. We want a 1.5 molar solution, so we have to figure out how many grams of that sodium chloride we need. So we're still using our big M equals moles over liters. So we plug in our numbers. We got 1.5 equals moles, because that's what in order to get grams, we have to go through moles, so that's our unknown. If you have problems with moles or liters in your unknown spot, you can put an X. It does not hurt our feelings. Times 0.2. So when we do that, we have 0.3 moles of sodium chloride. So we multiply by the molar mass of sodium chloride, which I told you was 58.4428. And we find out we need 17.53 grams of sodium chloride. So if you're making the solution, you would add your 17.53 grams of solution, of sodium chloride. You add that in 200 milliliters of water, and you end up with your 1.5 molar solution. The next way we can prepare solutions is if we have a stock solution, and this is using our dilution formula. I cannot stress enough that anytime you're working these problems, you have to underline the numbers given in order to help you identify what formula you're using. So I have a 2 molar, I see 100 milliliters, and I see 0.4 molar. So right there, when I see 2 M's, that must mean I'm using my dilution formula. And it does help that we're looking for milliliters, which is a volume. These 2 numbers that are next to each other, that was a common mistake when I was grading things. The numbers that are near each other, that say of or in or whatever words we use, they're near each other, they belong to each other. So plugging it into our MV, whoops, I have to change it back to my other color. MV equals MV. I have the 2V equals my 0.4 times my 100. In this problem, you do not have to change your milliliters to liters, unless I ask for how many liters you need. If it says how many milliliters and I give you milliliters, I'm keeping you from having to convert between units too much. Isolating our V using basic algebra, if you have to write an X there to know what you're doing, go ahead, is 20 milliliters. Because we multiplied the 0.4 times 100 and divided by 2. Okay, the next one was mole fraction. Mole fraction is very similar to percent composition. How much of a solution is one thing or another? So the X tells us you're looking for a mole fraction, and your N stand for moles. Remember that from the last unit. So this particular one, okay, so let's look at our numbers. We got 1.25, and we have a 4. So I want the mole fraction of each component. So we do have two problems here. The first one will be 1.25 over 1.25 plus 4. If I had 5 things down here, you're going to put all 5 on the bottom. This particular problem just has 2 components. You can have 5 components. You can have 10 components. It doesn't matter how many components you have. Your total goes on the bottom. What you're looking at goes on top. When we divide that out, we get 0.238. And I wanted each component, so I have to do the other thing. And that gives you 0.762. Notice that these two things added together add up to 1, so you know you've done your math correctly. If you do not add up to 1, if the 2, 3, 4, 5 things don't add up to 1, then you've done something wrong. And this is one of the few things in chemistry that have no unit, so you get to have naked numbers in here. The next one we talked about was molality. Molality is like molarity, and that you got your moles or your solute on top, but on bottom you have kilograms of solvent, and it is a little m, not a big M. I always remember the molal, the L in there tells me I'm looking at my little m. So I want to know how many grams. I see how many, that's what I'm searching for. I also see a number of 500 grams and 0.06 molal. So what that means, when we look at our formula, is I got 0.06 on this side, 500 grams, but it has to be in kilograms. So the magic number of movement is 3, 1, 2, 3. So we have 0.5 on the bottom. Mole is what we're looking for. How did I know that mole was my unknown? Because I want to know grams. The only way I can find grams is through moles. So when I do my basic algebra and cross-multiply that, I find out that 0.06 times 0.5 is 0.03 moles. That's not what I want to know. I want to know grams, so I have to multiply by the molar mass of potassium iodide, and that molar mass is 166.0023. And when you multiply those together, you get 4.98 grams. And the last one, talking about colligative properties. Colligative properties, delta T is your change in temp. I is how many pieces it breaks apart into. K is a constant from a table. You will be provided the table or the constant specifically. And the little m is your molality from the last slide. Sometimes you have to calculate molality before you can substitute in here. This particular one, I already gave you the information in molality. So we're going to look at our delta T equals I. We have sodium chloride, that's 2 pieces, an Na and a Cl. The boiling point for water, if we don't tell you it's anything else, then we're talking about water. The K value is 0.512 from the table provided, or information provided, and our molality is 1.5. That equals 1.536. That's your change in temperature. I want to know what the boiling point is. Because we are talking about water here, again, if we don't say what it is, then it's going to be water. Your actual boiling point is your original boiling point plus your change So it's 101.536 degrees Celsius. Freezing point is the same thing, you just have a different constant. So delta T is equal to 2 times 1.86 times 1.5. That gives us 5.58. That's your change in temperature, not your actual temperature. So your freezing point is going to be 0 degrees Celsius, the natural freezing point of water, minus, because we're lowering our freezing point, 5.58. So our new freezing point is a negative 5.58 degrees Celsius. Hope that helps.